Thank you, Sweta, for the nice introduction. So I'm Milan Shrestha. I'm a senior researcher at Continental NTU Corporate Lab from Nanyang Technological University from Singapore. And today I'll be presenting about this printable transparent conductive inks that we made, which can be coated on highly hydrophobic dielectric elastomers. And it can be used for various kind of applications like sensors, soft actuators, and so on and so forth. So today, I'll briefly describe you about the various kind of applications we are focusing on, but I'll focus more on the smart acoustic observers. So as I mentioned before, we have been working mostly on the elastomer material, which are basically the dielectric or insulating form of elastomer materials. And to convert them into some kind of sensors or actuators, we basically need to sandwich them between electrodes. And thus, this electrode also needs to be compliant or stretchable. And once we can sandwich the dielectric elastomer here with the electrodes, sometimes we need protective coatings as well. And we can make various kind of sensors, for example, the strength sensors that can be used in haptic gloves. We can make some form of touch or force sensors for display panels. And we have also worked on various kinds of non-conventional applications like making humidity sensors purely out of dielectric elastomer actuators. So maybe I'll discuss a bit on what is a dielectric elastomer actuator. Our dielectric elastomer actuator is basically a dielectric elastomer sandwiched between compliant electrodes. And when we apply the voltage between these two electrodes, because of the Maxwell stress, it will squeeze the elastomer, causing expansion of the area of the elastomer. And this expansion can be used to make various kind of actuators. For example, we have worked on soft robotic grippers based on minimum energy structures. We have also worked on various kind of transparency tuning devices, which is mostly by manipulating the micro wrinkles of transparent electrodes on the dielectric elastomers. We have made various form of tunable lenses there. And also we have worked on smart acoustic observers. So more on smart acoustic observers. I'm sure a lot of us here might not be familiar with the term. And so I'd like to explain what is a smart acoustic observer and why we need it. So imagine you're sitting in a house, your house is nearby a road, a car is going on the road, right? Based on the speed of the car, is going to produce various frequency of sound. And most of the acoustic observers, they are opaque and are used in the walls, but windows, we don't have good capability to block the noise. And especially if the sound is of very broad frequency range, then most of the transparent observers cannot handle this. There are some transparent observers like micro-perforated panel observers, which have perforations like this. But in passive form, their absorption bandwidth is quite narrow. So to solve this problem, we worked on a micro-perforated panel observer, which is where the micro-perforated panel itself is made out of dielectric elastomers. So this is a dielectric elastomer actuator with micro-perforations. And upon activation of the dielectric elastomer, the perforation size here can be reduced. So by tuning the size of the perforations, so you guys can't see my, okay. Here, by changing the size of the micro perforations, you can tune the peak absorption frequency of this kind of acoustic observers. But the problem is, imagine a stressed polymer with numerous holes. Eventually, it's going to rupture, right? So the reliability of this kind of smart acoustic observer is not really good. So to solve this issue, we thought of using a dielectric elastomer actuator in a form of bending actuator. So we sandwich our non-prestressed dielectric elastomer to a stiff, flexible substrate like Milan or polyester or PD sheets. And then when we activate this device now, is going to bend like this. Instead of opening up, it's going to bend, and this bend helps us to increase or decrease the open ratio of the acoustic observer. So we solved the acoustic observer problem, but what is the another problem? So the another problem is making it transparent. To make a transparent acoustic observer in a more scalable way, we need to make sure all the electrodes are transparent as well. And one of the big problem is there are very few stretchable transparent electrodes. Some can be made by formation of the micro ring tools, but they will not be that transparent because it will diffuse light. And there are some sources of nanowires, but the process of putting nanowires on very low surface energy elastomers like PDMS, acrylic, or SCBS is quite tough. And so the most straightforward approach would be to use some form of ink that can be directly coated on low surface energy dielectric elastomers. Yeah, but the problem is if you coat an aqueous-based ink on a low surface energy elastomer material, it will form non-uniform patches, right? The connectivity and the overall coverage of the area would be very bad. So there is a way to solve this. That is simply by doing the surface treatment or plasma treatment. But for our applications as a dielectric elastomer, first on acrylic and SCBS, plasma treatment doesn't really work. And on PDMS, it works, but the time it works is varying. So with time, its surface energy will be lost again. And in addition, it can form a brittle top layer, which can crack upon stretching, and which will reduce the reliability of the whole device. So we thought, okay, maybe we should make a form of ink that can be directly coated on this kind of low surface energy elastomers. So this is what we came with, and this is what I'm presenting today. So how do we make the ink? The ink is basically made of PSS. I will not go in depth because most of you are familiar with the PSS, which is a form of conductive polymer. We form an aqueous form of this PSS by ultrasonication, and then we mix PDMS part A, part B, along with Tritonex, and which is a surfactant, and ethylene glycol, which can enhance the electrical conductivity of this whole solution. So after mixing it, we get a viscous ink. When coated, it can easily be coated on the any of the low surface energy substrates, and this is how we make the bending dielectric elastomer actuator. This is a Milan sheet. We laminate it, and then we coat the ink. After coating the ink, we cure it, and eventually to give it a different kind of shape to open up, we do laser cutting. And as I said before, we focus on making how this process scalable. So we try to optimize this ink for screen printing process. The ink that we develop, when it's stored at 4 degrees centigrade, the viscosity it didn't change much even after 30 days. Maybe it will be stable even after a few months, but I do not know. I haven't tested it. And we have tried to optimize it for various screen printing stencil or mesh counts, and we obtained about 1 kilo per square kind of seat resistance with about 100 mesh counts. And this ink, this film is as transparent as 80%. Talking about the morphology of the ink, I think it's not so straightforward. So when we coat and cure the ink, what we found is that there is some kind of layer segregation, and the top layer becomes the insulating protective PDMS layer, and the interfacing layer to the substrate is actually the conducting layer of PSS, and then the base layer is our substrate. And how do we found out this is by doing cross-sectional Raman spectroscopy, and we could tally the peaks with peaks of the cross-sectional spectrum we done here with the PDMS, and here with the PDOT, and this is just the substrate material. We also found out that there is some form of shipping of PSS on the PDMS layer, but only at the interface. And going to the dielectric elastomer basic evaluation of basic dielectric elastomers made with this ink. Conventionally, dielectric elastomers, they were made using either carbon grease or graphite powders. So this is the most widely used electrode for dielectric elastomer actuators. And we have compared our ink with this electrode. And as you can see here, this is a device made on the 20 micron PDMS here. So we found out that because of the seepage of the pure PSS on the very thin PDMS layer, it increases the leakage current when applied volt above 3.5 kilovolts. However, we also, while trying it out on a thicker film, here VSB 4910 is a 1 mm thick acrylic double-sided tape. So when pre-stretched, it is around 200 microns. And we found that actually the actuation strength is quite comparable to the conventional graphite electrode. So we can conclude that for a reasonably thick film, there is not much compromise we need to make. And as I mentioned before, we try to use the bending form of dielectric elastomer actuator for this device. And this is how it looks when we activate the device. So here, the video shows only one section of this cut. And we have some form of dielectric breakdown when we try to apply voltage above 6 kilovolts. So for all our applications, we try to restrict the application voltage to below 5 kilovolts. And we are able to obtain quite good tip displacement. The tip displacement maximum we can obtain at 5 kilovolt is about 5 mm. And this is the final form of the acoustic absorber. The final acoustic absorber, it consists of a front microfluidic panel, behind the blue one. This is the bending dielectric elastomer actuator made with the screen printed or blade casted electrode, and there is a back cavity, which in combination forms the smart acoustic observer. And we activate the device. Let me try to play the video. Okay, so when you activate the device, it opens up like this here. So we have an array of 25 cross slots, and when we activate the device, it will open up like this. And this change in open ratio with about 5 kilovolts is almost 12%. And the absorption spectrum of this acoustic observer at the voltage of state, that is like when this is completely closed, it has a peak absorption frequency of around 700 hertz. And when we activate the device at 5 kilovolts, the whole spectrum is shifted, and then we have a peak absorption at around 1200 hertz. So we can shift the absorption spectrum by about 70%, and in this way we can get a much broader acoustic absorption. So to conclude and summarize, today I showed that we made a transparent conductive ink that can be coated on low surface energy elastomer substrates, and it can be used for various dielectric elastomer sensors and actuator applications. Yeah, so this is the end of my presentation, and then I'd like to acknowledge our funding agent and Continental NTU Corporate Lab for supporting this research. If you guys have any questions, you can shoot me now.